And hello everybody and welcome to the live stream. I assume everybody's seeing me since I'm getting feedback. If anybody's, would somebody tell me that they're hearing me well and seeing what's going on and seeing my terminal that says, Prolog class and that life is good. Oh, it says is there anybody? Okay. Tim says he can hear me. Tim, would you tell me what you're seeing just so I can do it quick? Okay. All right. I'm going to assume we're working. Good. And we'll proceed on then. So tonight I wanted everybody to have a chance to see and work with a Prolog program before we really got to have got into the details of Prolog. So if you'll navigate to whatever directory you have the adults and children in, if you're on Windows, you can just double click on that file. And if you're on Unix and you've been using SWIVM, you can do SWI-Prolog and adults and children. If you just provide a file name with SWI-Prolog, it will consult that file. So I have mucked with my install enough that I have broken various things. And now I'm at this this question mark minus sign, and that is the query prompt. The query prompt is Prolog is a query language. You establish a knowledge base, you tell it some rules and facts about the world, and then you ask it to prove things about the world. And in this case, I'm going to ask it to prove that edit is true, which always is true, except and has the side effect of bringing up the editor window. Okay, and I will pull this over and maximize it. Okay, this is a little program, and you should all be following along. So if you haven't done that, then SWI-Prolog, SWI-Prolog, space, adults and children, the file. And you should do that from the directory you've stored your file in. Okay. Going to look at the code just a little here. This is the equivalent of the Java package statement. This tells what module these predicates will go in. Prolog actually dates that file. You should download from the Moodle site. It's right below the link to this, or right above the link to this live stream. Is everybody good? Do people need a moment to grab that file? I suspect most people have got it. I'm going to go on. Yeah, and you'd have to be logged into the Moodle anyway. So, okay. Okay, so if you'll all repeat what I just did, that is, start SWI-Prolog with adults and children, from then and do edit. We'll go on. Okay. So, prologue. You'll notice that the very first thing is colon minus, which is a which is makes this a directive. You can insert arbitrary code into Prolog, and this happens to be arbitrary code executed at consult time. Prolog, having its background in AI, consults its knowledge base. So this is the name of the module, adults and children, and we export one thing. This notation is go with 0 arguments. This is a common notation in Prolog, and that's all this exports. Then there's a comment. This little bit of ceremony is the marks this as for the automatic the literate programming autodoc style generator. Now to the problem we're going to solve. We have a this is one of these classic crossing the river problems. In this case, we have 3 adults and 2 children and a dog, and all want to cross the river from the left to the right. They have a tiny boat. The boat can take a single adult or 2 children or a child and a dog, or of course you could leave one space empty. And the problem then is, how can we get everyone across the river? So fairly straightforward little problem. So the way we'll do this, all right, and of course I'm not expecting everybody to follow all of this. This is intended as a first glance, so that when people do start studying, they're not hearing about concepts in a vacuum. They can go, oh yes, I've seen this before. So since Prolog is a query language, we'll always start by querying something. And I've made a predicate called go in Prolog. Things that might be functions in other languages are predicates. And there are some differences between a predicate and a function, but You can think for the moment of these as functions. I've made a Go, which will grab the initial state of the world. From that state, construct a plan, and then write the plan back out. Now, when we get to this stage, of course, there's probably more than one way to solve this. So, Prolog, after it solves this, will give us the chance to back up and solve it using a different proof. That is, solve it in a different way. So I'm going to demo doing that. Okay, here's a solution. You can try this. And you'll see you get number of people on the left bank. This is adults, children, and dogs. And then number in the boat, adults, children, and dogs. Number on the right bank, adults, children, and dogs. And we get a solution. At the bottom, we say true, because Go is something we could successfully prove. If I now type a semicolon, I get a different solution. And it went by pretty quick, but hopefully you can see that the last thing here that happens is the two children end up on the left bank alone. They get in the boat and row over to the right bank. If I scroll back up, I'm just scrolling now in the terminal, you'll see that the last thing that happens is one of the kids and the dog end up on the left bank, and the kid brings the dog over. So if I continue to hit semicolon, I'm going to get different solutions. And you can see these different solutions mostly consist of bringing the dog over earlier. See, now we've got the dog coming over quite early. And then at some point, we run out of solutions, and we ask for more solutions, and they say false. I can't find any more proofs of this. Okay. Are people confused by that? Did that make sense to people? Yes? Your chat is the only feedback I've got. Otherwise, I'm just talking to myself. So, okay. I think everybody was good, because that's all I can assume. All right. So what happens here, we're going to go in, and what I'm going to do at this point is I'm going to run it again, but I'm going to invoke the debugger. Okay. The way you invoke the debugger, I'm going to ask it to prove two things that are anded together, and comma is and. So the first one just invokes the debugger and puts us in single step mode, and the second one invokes the program. So I'm going to put, if you do this, you should get this little debugger window, which I'm going to maximize now, because we're not going to actually look at the window at the terminal for a bit. And you'll notice Go is green. That's where I am in the program, what I'm trying to solve actually. At the moment I'm trying to solve Go. And you'll notice up here I have what looks at the moment like a pretty normal call stack, but will at some point quit looking like a normal call stack. Now, space gives you a chance to step into the project, and S gives you a chance to step over. So this is pretty much like any debugger you've used. However, this being Prolog, I can do something kind of bizarre. Let's say I go in and I'm just going to make a couple of steps now, and gosh, I realize that crossing plan, I wish I had gone in instead of over. If you hit R, since this is a stateless language, anything, as long as you don't do anything that altered state or did I/O, you are able to hit R and retry the predicate. So I'm going to hit R so we can go back, and all the computation we've done has been undone. This actually was probably a fairly easy thing to implement, because it's a normal part of how Prolog operates, with this notion of being able to back up. So this can be very disorienting if you're used to a deterministic language. Okay, so I hit space again, and I'm going to attempt to prove go. This construction, this operator is called neck, says that go is true if these three things are all true. Yeah, R vastly speeds up your debugging, because it means you don't have to decide, am I going, yeah, it's time travel debugging, and it's just beautiful, because it means you can run across all the high level stuff, see which one broke, which a really common way to have a bug in Prolog is to just have something fail. Okay, so I am going to attempt to prove all of these things, because they're connected with commas. Go is true if they are all true, with and. So, okay, I'm going to see, and notice that there is no value for init. We've not assigned it a value, right? We never really assign things. Variables in Prolog are closer to variables in high school algebra. The exercise program, the exercise problem, find the value of x. Well, they really mean find the value of x that makes this true. And so what would make init true? Well, let's look at how init's defined. It turns out init is just defined by listing the things that make it true. If its argument is this, which is a structure. Yes, Tim. The phrase "go is non-det" is actually for the literate programming system. You can document whether things are going to have more than one proof or exactly one. If I'd said semi-det, it would have assumed there was 0 or 1. If I said multi-det, it would have guaranteed 1 or more. But we have no real for example, we have no real proof that this is a solvable problem. Suppose I only provide one child. Is that solvable? Well, I can probably think it through and realize it's not. But if I did start with only one child, this isn't a solvable problem. You can't actually get everyone across the river with only one child. You need them both. Okay, so if init is this thing, which is a compound term. Okay? Clarkson and Mellish call this a structure. That terminology is largely dead. Almost everyone will call this a compound term. The one drawback of using Clarkson and Mellish is that the book is almost 30 years old and the vocabulary has drifted a little. It's not unusual when working in Prolog to run into things that are kind of historical because of the age of the language. The language dates to 72. Okay, so if I'm going to step over init, and hey, init is now, as we call, ground to or bound to this compound term, which is 3 adults, 2 children, and 1 dog. And this was just my way of being a good software engineer and abstracting the initialization information into one place. Effectively, the init is my way of making a constant. There are no kind of dedicated constants in Prolog. In the sense of like, and you might have an enum in a different language, or like in, C, where you pound define something as a 42. So, okay. So now I know my initial conditions, and my initial conditions are boat on the left, 3 adults on the left, 2 children on the left, and 1 dog. And I must say, I probably should have provided that up in the module comment. I actually describe it in the crossing plan. States a list of left, meaning the boats on the left bank, children and dogs, and right. And notice my encoding I've chosen is that these will be the numbers on the left bank. Okay? So the right only says that the boat is on the right bank. All right? And here, now, I am going to ask, what is the crossing plan? Well, the crossing plan takes a list of states that the system has been in so far, and returns. Plus means I expect this variable to be bound, and minus means I expect this variable to get bound by the predicate. That is, for example, so these are called modes. Now, to return to your question, what I'm doing is I'm making a list of the states we've been in. And of course, we've been in the initial state. So I'm going to pass that list in. And this list, I'm going to make the list longer by inserting things on the head, on the left-hand edge. But that's just because these lists under the surface are Lisp-style lists. That is, the easy operation is consts. And having consts, and so it made sense to get the current state be on the left. Okay, now, crossing plan. Crossing plan, of course, requires that a crossing plan is a predicate, so we're going to attempt to prove crossing plan, and we're going to attempt to prove crossing plan for a list of initial states. That is there a crossing plan if you've been if you've already done this list of things. And if there is, then what is that plan? Do you guys know the notion of constructionism? Constructionism is kind of a philosophical thing. What constitutes proof? Well, one thing that constitutes proof is showing something, right? If you're a strict constructionist, then you have to be shown something in order for it to be true. So, for example, you don't believe in proof by contradiction. Excuse me, my cat wandered in, opening the door to the room with the loud machinery next door. I'm going to shut it so that I don't have that in my microphone. I'll be right back. Okay, and I'm back. Tell me if I've just messed up my sound. I'm hoping I haven't. So, Tim, did I answer your question of why it's in a list? The list syntax is just yeah, are you guys hearing me? Somebody heard about the kitty, so. The crossing plan, when it returns, will, yeah, I'm sorry, Gordon. Gordon, what comes in is a list of states, and what comes back out is a list of moves. So the moves are actually going to be of the form LR or RL and the number of people in the boat each time. Yeah, I'm aware of the delay. The video quality is much better if I allow that delay. Okay, so here, in fact, I'm going to hit S and not worry about the details of how it proves there's a plan. I'm just going to get one. And notice that now, before, plan was an unknown. It was not bound. Now, I double-click there, and now this is a list of all the moves. And again, it's the adults, children, and dogs move for the three arguments. So the structure in it, hang on, I'm going to go back here. So what's happened is I've asked, what would make init, what would make this variable init, what would we have to set it to? What would it have to be for init1, the predicate, to be true? Well, in this case, I've simply listed the things that would make it true. And there's only one of them, and it's left 3, 2, 1. Does that make sense? It's a little odd. It's like, it's a bit like pass-by reference in C++, but more that I'm figuring out values. That is, suppose I make the assertion that 11 is the largest prime number. You can prove that it's not the largest prime number by pointing out that 13 is prime. So yeah, we don't, so Prolog does not have Boolean functions. Prolog has essentially void functions. Everything's void. There is no, this isn't, you know, it's not meaningful to put something in on the left. Okay, so I now have a plan, and I'm going to use R again and come back in because this time I want to go in. Okay, so what happens when I go into crossing plan? And I'm going to not really worry about, you know, kind of the details of this particular program. I want to show language features. Okay, we have asked what will make crossing plan of the list left 3, 2, 1 true. If you look over here, you'll notice we've got a couple of new call stack frames, which is interesting. We actually have 2 of them at this point, because the first one is I have several clauses. Each of these is a clause for crossing plan. And the first one says, the first one is a rule for lists that start with the boat on the right and no one on the left bank, and any past history you want, and gives as a plan the empty list. Can anybody tell me what this handles? What's going on here with this first one? And sorry, I always have to they are, and in fact, pattern matching in SML is a unification-like pattern. Yeah, Tim, it's termination. It is the we're at the goal. There's no one on the left bank. The boat's on the right bank. We're done. So we're going to say that a valid plan, if you start with everybody on the right bank, is to do nothing, which is a true statement. But now we look over here and we go, okay, now we have for the left, for the boat on the left, if we have any number, an arbitrary number of people, and now below there's one more clause, if the boat's on the right and we have an arbitrary number of people on the left bank. So Erlang was originally implemented in Prolog. Joe Armstrong posts something about Prolog at least once a day. The vertical bar is cons. So everything to the right of the vertical bar is the rest of the list. So past is going to simply be the rest of the bits. Yes, Tim, the state that gives the boat's location is we have a list. We have a list of all the states, and whether this is left or right is the boat's location. Yeah, ZZZ is correct. Yeah, and the A, B, C are number of people in the left bank. Okay. I could have called them all boat and said left or right, and then A, B, A, C, D, but this made as much sense. Okay, now we define that we could have a crossing plan for the current situation where the boat's on the left, and there's some past history. If we could figure out a new move and a valid plan for the reduce problem. Now, this is a library function that's quite frequently used called member. And member successively gives as solutions all the things that are members of a list. So I'm going to step over it, and the first thing it gives me is the first member of the list. What I've done is, at any given stage, there's really only, if you're on the left bank, there's really only 4 possible moves. And hang on, I even have a slide for this. Okay, these are the 4 possible moves. Move an adult across, move a pair of children across, move a child and the dog across, or just move one child across. And in this case, it's given us the first of these possibilities. It said, let's just try assuming move is LR100. Oh, hi, hello. Yeah, I know you from Twitter. Okay, what does LR100 mean? It means we move one adult across. Now, is that going to work to start by putting an adult in the boat? Okay, well, let's find out. I want to be able to hang on to it and call it move. So I will ask you to prove that something is the same thing. That is, these must unify. It always tries in the same order. In this it does, yes. It's going to depth first search through the solution space. I'm always going to try moving the adult first. And in fact, a particularly poor choice of this order, and the order will affect how rapidly this executes, a better choice for me would have been to place 2 children in the boat, not send a child over alone, because that's a suspicious move. Yeah, if you have an adult go alone, there's no way to get the boat back. Okay, now we've proposed moving some people over, but remember we need to have enough people to do this. So that's a constraint, just the real world. And in this case, we do have enough people. And now I'm going to take this move and this state and ask, what would be a new state? And of course, this is going to be a deterministic call. I will step into this, and we're going to have fewer people on the left bank. By the number of people in the boat. Now notice what I've done here is I've got a bunch of things I don't know, right, new A, new C, new D, and I fill them in as I go along, despite the fact that I've already mentioned them. Just because I mention them doesn't mean I know their value yet. They might be unbound. And so things are always running around unbound. All right. Now I've got another problem. I don't want to, like, send 2 kids across, send 2 kids back. Send 2 kids across, send 2 kids back. So I have to, that's why I'm hauling my past with me. Now, since the past in this case was referred to as the rest of it, and I wanted the first element, so I wrote it out in this way. I have to write it out the same way again. I could have done the same thing I did with move, just to avoid doing that. But in this case, I chose to just go ahead and write it out, since I only need it once. And I'm going to ask, is the new state already a member of the previous states? That is, have I been here before? And it's red, which means no, it's not. This is, it is not provable that. The it is not provable operator. And because I have negated this, there's no true negation, but it's not provable that. This gets into the open and closed world assumption. We seem to be fine. The boat on the right and 221 is a new state. So now we recurse. Yeah? And if there's anybody who doesn't know about recursion, say so. We'll stop and talk about it. But or I'll make certain there are exercises. So now we're going to pass a new state. Why is it they changed from not to \+? It's because the semantics of this can get complicated, and \+ is not provable. Honestly, it's mostly historical. I can't believe anybody would choose that today. Remember that this language, much of its syntax was solidified in 1980. And the parts of the language, in fact, including that, I believe, date to 1972. SWI-Prolog only got strings in 2012, 2014, relatively recently. Don't worry, there was string representation. There just wasn't a true string type. So now I'm going to ask, well, what would, after I move to that new state, what would be a valid plan? And I'll step in. So now notice that I have a stack. And notice that I'm keeping, I now have at least 2 cases. Hang on, I'm going to do this next one. And notice that I'm beginning to accumulate places where I might have had the road not taken. These are called choice points. The meowing in the background is legitimately part of the class. That is underscore the cat, and you'll all appreciate the name underscore later. So here, we're now on the right bank. Since the left-hand edge of the list is right, and it's not the goal, we're going to match with this one, and we're going to fill in A, C, and D. And now there's really only two things you can do on the right. Now notice that just because I have search doesn't mean that I can be kind of the brighter I am, the faster it runs. So in this case, you know, there's no point in yes, underscore is the anonymous cat. There is no point in moving either a dog or an adult back to the left bank, right? I hope you can see this. Basically, you're going to have to use a child to get the boat back. So what you do with the children is interesting, but the adults always just move from left to right, and same with the dog. So the only real choices are move one child back or move them both back. So, okay, we're going to try and move two children back. All right. As for the previous clause, as for the other clause, I just want to be able to hang on to move without typing this awkward RL, boat A, boat C, boat D. And now I need to know how many total people I've got. So I'm going to evaluate the init again. And in this case, I know that it's going to be on the left, and I really want the individual numbers. So I asked it, hey, what three numbers in a left structure would satisfy init? And it tells me the three numbers. That way, you'll notice I'm an awful lot of things that I might have to extract members or index arrays. They're all coming out kind of with this unification. It handles so much of the code. And now, once again, we have to make certain that we've got enough people on the right bank to actually make the move. And there are no adults on the right bank, and we're not going to put any in the boat. But here, oops, I sent one child over, and now I am proposing to send two children back. So when I hit the space bar, it's going to fail. It can't do that. It says, okay, that's not a valid solution. So it goes back to where the last choice point was, this member. And this is where the last place that I had a choice. Remember, I could have sent two children or one child. Tim, to answer your question, yeah, there's only one piece of data. It is going to be 321. It's actually just good software engineering. If I want to change the number of people in the program, if I've just scattered 3s, 2s, and 1s throughout the program, it's going to be very painful to change that, especially if this is some large, real program. So, I mean, you've been taught in other languages to use symbolic constants and not just scatter 42s throughout the program. the same is true in Prolog. You know, it's better to have a predicate that gives you the constant. So, okay, we've failed. So we backed up, and now we're going to try moving one child back. Again, I'm going to hang on. I'm going to make move be the whole move. I'm going to have to get the number of people in the scenario again. And now, I still don't have enough children to move this back. Remember, we sent one adult across. So, if you've got one adult, right? This is Gordon's comment. No way to get the boat back. So we've run out of solutions here, because that was the last thing in the list of moves. When I hit space, watch what happens to the call stack. We go back up to the last place we can find the last place we can find a choice point. And it actually turns out that maybe they're thinking we can match this to some other way of making a crossing plan with new state, of course, is right 221. So our crossing plan is right 221 and left 321 at this point. So there really isn't. At this point, we thought we might have we might be able to save ourselves, but we can't. So at this point, we're going to go all the way back up to the previous member and try a different tactic for our initial left move. I will try sending one child over. Is that going to work? Well, it's a valid move. And remember, we backed up. So we're back to the list of states only being the initial state. The new state is 3 adults on the left bank, 1 child on the left bank, and the dog on the left bank. That is a new state, so that's good. But now, what's going to happen? I will drop in. My past is 321, and now I have this right move, 311. I'm going to try and move 2 children back. Yes, the Garden of Forking Paths. Prolog uses SLD resolution, which is essentially a tree search. You can think of it this way: if you don't run into a control structure in Java, you are going to execute from top to bottom inside of a method. In Prolog, you are going that kind of built-in execution order is a tree search, a depth-first tree search. Okay, I will attach the move. I will get the total because I'm again on the right bank this time. This time with 1 child, and I don't have enough children to send 2 back. So I'll go back. I'll try to send 1 back. And that actually we have enough people to do. And we can figure out what the new state is, which is going to be 3, 2, 1. Now what's going to happen? That's going to fail. And since I had no moves from the right bank, it fails all the way back up to the caller. And since the caller thinks it's got more choices, it actually doesn't. It's going to stop there. So when I hit space, it's going to fail again, and it's going to fail back to member, giving us the next opportunity. Send 2 children over. And we've all kind of like seen how this actually works as humans by this point, and this is a good move. Send 2 children over, and then one of them is going to bring the boat back. We have enough people on the left bank, because we're back at the start state, to do this. And it produces a new state. And so I'm going to step in, and we're running a little long, and I'm going to step over, and it's going to try and bring 2 kids back, and that's not going to work because that returns us to the initial state. And now I'm going to hit S at this point. I'm not going to recurse in because I think this is getting repetitive. So now it's given me the entire rest of the plan. And notice this is not the whole plan. This is just the plan from the point I'm in. So, and notice my stack contains this useless choice point for crossing plan, and called a member for each direction all the way down to the bottom. Notice this is a useful UI thing. You can click around in this and go up and down in your stack and your trail. So hang on, let me figure out where I am. Where am I? There I am. Okay, so at this point we've got one. I'm going to hit space just because it's stopping on exit. And I now have a plan. And when I hit space, I now have a valid crossing plan. Okay? And right plan, I'll kind of leave as an exercise for you guys because this is pretty much, excuse me, I'm going to turn my carpal tunnel preventer off. Sorry about that. And we're now, this is relatively straightforward. It doesn't leave any choice points because there's really only one way to write the plan out. So when I creep, it says it's not waiting, which means I'm not actually in the debugger at the moment. I'm back here, and remember, it's now waiting for me to hit the semicolon and give it another choice. That's going to drop me back in. Well, write plan doesn't really have any choices. So when I try and get another choice for write plan, it's going to back up. So it's going to back up and try a different plan. And what we've just seen, I hit S instead of going in. My apologies. But now, I believe if you look at it before, the last thing that happens is one of the kids returns and gets the dog. And now, the last thing that happens is one of the kids returns and gets the remaining child. It ends up with both kids on the left-hand bank. And now, if you get into this situation where you're not seeing interesting stuff, you can hit L and it will continue execution without. And that will go on until you hit another G trace. You can, and now we're not waiting. And at that point, you pretty much close the thing. And at this point, the debugger's been deactivated, so we just get solutions. And if I hit this a few more times, I get to false. I would say there is a second way of invoking the debugger. Just if, for example, I was having problems with write plan, and I didn't want to keep stepping in until I found it, I could say tspy and in a very Prolog-ish thing to do, notice I don't have to say write plan 2 because it will do all of everything that matches write plan. Prolog is oftentimes writing little expert systems everywhere rather than trying to force people to do it right. It's the easygoing language where, for example, many places where you pass a string to library predicates, there are several library predicates, and forgive me, I'm running a couple of minutes over. I'm wrapping up here. Many places where you have library predicates, and they take a string, they'll take an atom or a code string or a real string, and you don't have to worry about what it is. This is convenient. File paths can be represented in a number of ways, and those usually you can be passed interchangeably. And then within it, you just dispatch by unifying or guarding. You put a piece in there. By the way, if you have SPI points, let me show you that they're a handy tool. This is the built-in editor. There is an edit breakpoints. So if I want to get rid of that, you can use no SPI with the name of the predicate, or you can do that. And forgive me, I'm going to show you a few other things that are just really cool that you'll want to know about later. You can set up so that rather than throwing an exception, it stops at an exception and lets you debug. There is, this is going to look funny because of the big font I used for the streaming, but this is a real-time graph of memory usage and CPU usage on a per-thread basis. And later on in the course, we're going to talk about this extremely cool window that is an intelligent debug message and logging message monitoring tool. So you can put in debug messages and then only turn on the ones that are relevant to what you're doing at that moment. Okay, I'm closing the window, and I'm going to type halt. Halt is a predicate that causes the system to exit. Any questions? Great, great. I'm glad people are having fun with it. Prolog's kind of amazing. I I must confess, I personally have kind of damaged my life when I discovered Prolog, because it's at the moment quite difficult to get a good job writing Prolog, and I just have gotten to where I'm reluctant to write anything else. Yay! So I hope I've enthused you in a bit. Yes, standard Emacs can be configured. I'm gapping exactly where it is on the website. I put a link to it in Prolog installation somewhere. There's somebody asked that question in one of the forums, and if you just a minimal amount of using the search box will also find it. Hey Danielle, I hadn't seen you up here. Glad you made it. Yeah, it's a real trip. Anthony, I hope your textbook. Yeah, Gordon, if you're an Emacs fan, the little PC Emacs has the advantage that it's actually running in the same VM as your program. So, for example, syntax coloring is authoritative, and there's great integration, as you've seen. But the downside is it's a sucky little clone of Emacs. It's even got some kind of annoying bugs in it, and nobody's ever going to fix them. It is an ancient system that is slated for replacement. If somebody came up with a way for me to live while I did it, I would probably be writing a replacement right now. Yes, there will be, Daniel, when I turn on week 2, which I think I'll probably do tomorrow. The assignment for next week is going to be chapters 1 and 2. And then we're going to have a bunch of content that we're going to have hand puppets. I'm going to this unification and SLD resolution can be quite baffling, and it's usually explained in rather stilted mathematical terms, and that I don't find that useful. I'm not really a mathematician. So my explanation of it uses hand puppets. which hopefully will at least be friendlier. And really, it's a query language. You're always having a conversation. You ask something. Hey, Maxim, yes, the editor does support a dynamic error highlighting. I'm having great fun teaching the course. I'm working like heck, but I'm having great fun doing it. People have been contributing, and it's not enough to live on, but it's enough with that it's keeping me going for a little while, and I am expecting to get a job here pretty soon. Yeah, so hand puppets. Next week is hand puppets and mind bending, and you hopefully got a taste of mind bending this evening. And hopefully a taste of why I love Prolog. So, okay. I'm going to wait about a minute and see if there's any other questions, and if not, I'll be wrapping up. Yes, I will post a picture of underscore on the Moodle. Yes, and underscore is, of course, usually I'll tell you the story. I'll tell you the story before we go then. Friends found a kitty under their porch and couldn't keep it, and asked us if we would like to have a kitty for the shop. I'm half of a kind of incubator experiment, building projects that combine manufacturing and mechanical stuff with software. And underscore and so we got the kitty, and we had trouble naming it. I don't know. You know how this always invokes social dynamics. And after 10 days, we had still not named the cat, so I announced to Kevin that in the next 3 minutes we were going to name the cat. And he still continued to hem and haw, this being very Kevin-like thing to do. And after the 3 minutes ran out, I announced that the cat still had no name. Therefore, it was the nameless cat. And in Prolog, if you need a variable but don't want to bother to name it, you can call it underscore. The reason this is important is that, of course, once you know the value of something, you don't want to, you can't unknow it. So these variables, once bound, can't be unbound, and that means you could end up having a whole bunch of these variables. Also, it's kind of, it clutters up your code. So if I need the fourth argument that gets returned from something, for example, hang on. Say there were operators, which you can define on your own, and I want their names, but it's going to give me two other facts about them, which I don't care about. Whoop. Maybe it's current op. Yeah. So, and I got the wrong argument. I got the precedence. But you see the point. . So these underscores are useful, and we'll be talking about them when we get to variables next week. Okay, folks, at this point, I'm going to call it. I will give this stream about a minute for you guys to catch up and ask last questions. Good night. Good night, everybody. Okay, and I guess that's it. Bye-bye, all. Thanks. I had great fun doing this evening.